So here we are, we're on number 5 at your handout. Let's talk about another function. We're still talking about limits. So remember when I had the instantaneous speed I was trying to compute, my problem with the algebra was that if I had a 0 in my denominator I couldn't take care of. So this is a similar, well, it's a function that's similar in the sense that it has this 0 in the denominator. So if I asked you what y is when x is 0, you couldn't tell me because we can't plug in 0 and then evaluate this function. We'd have sine of 0, 0 over 0. And with 0 in my denominator, it's not defined. But we can still investigate. Remember we said we can investigate limits with algebra, with graphs, with tables. So watch what happens if I were to follow along this graph. If I was walking along the graph and I was trying to walk toward the place where x equals 1, or maybe I was where x equals 0. Maybe I was walking in this direction. Even though I know there has to be a blank spot right there, because there can't be any point on this graph when x equals 0, because y is undefined when x is 0, it looks like it should have been y equals 1. Everything about this graph says it was moving toward that point, 0, 1. Everything from this direction looks like it was heading toward y equals 1. And I can investigate that with a table too. So you could set up your calculator to make a table of values. So I could plug in numbers that close to x equals 0 on the left-hand side of x equals 0, like negative 0.3, negative 0.2, negative 0.1. I could also plug in small values of x, values close to 0 that are on the other side, so to the right of x equals 0, like 0.1, 0.2. And if you look at these y values, they seem to indicate that as you were letting x get closer and closer to 0, y was going to get closer and closer and closer to 1. Now here you can't actually let x equals 0 because you'll have this undefined value. But as you came at x equals 0 from either side, you were approaching a y value of 1. That's why we say that the limit as x approaches 0 of sine of x divided by x is 1. And here's the notation that we're going to use for that. The limit of f of x as x approaches c is L. And you can see that that notation is written here in symbols and written here for you in words. So the way we would describe this situation that we were just looking at, the sine of x over x as x approaches 0, we would say the limit of sine of x over x as x approaches 0 is 1. This particular fact, this particular limit, to prove it using algebra is trickier. It's much trickier than the limit we did with the instantaneous velocity earlier today. So if you want to just memorize this function, this fact, this limit, that the limit of sine of x over x as x approaches 0 is 1, that's fine. If you're interested in the algebra behind it, you can read about the sandwich theorem in your textbook. All right, so I have good news. Some functions are what we call well-behaved. And when we're working with a well-behaved function, or a part of a function where it is well-behaved, to find a limit using algebra is just as easy as taking the x value that you want x to approach and actually just plugging it in. So we can use substitution. So this is example 4a from page 63. I'll read it for you. If I want to find the limit as x approaches 3 of the quantity x squared times 2 minus x, this happens to be a well-defined, well-behaved function, and we're going to talk more about what that means exactly in the next couple of sections. But notice I can plug in, I'm going to replace the x's with 3's, and as long as when I try to do that math, so I get 3 squared times 2 minus 3, as long as I don't break any math rules, trying to divide by 0 or take the square root of a negative number, I get negative 9 as my result, and that is the limit as x approaches 3 of x squared. 4b is also an example of a well-behaved function. This is my well-behaved function. If I plug 2 in for x, if I replace all the x's with 2 and I evaluate, so 2 squared plus 2 times 2 plus 4, I get 12 divided by 4, which I can simplify to 3. So I would say the limit of x squared plus 2x plus 4 all over x plus 2 as x approaches 2 is 3. You can see here some instructions for you.